All right, we're talking about vectors today, and a lot of real world math situations just involve a number that basically does all the heavy lifting for us. We have one number that is our solution or what we need to know. How far am I away from Chicago? I am 70 miles from Chicago. Or how tall am I? I'm 6 feet 2 inches tall. Just a number may get the job done for us. But if I asked, how do I get to Chicago, and somebody told me you go 70 miles, that doesn't do the job for us. So a vector it's much like a polar coordinate that we just got done studying. It gives us some idea of a direction and what it's going to refer to as a magnitude. I'm going to talk about, just maybe pushing a chair around a room and kind of on a coordinate grid. And for instance, this very first problem, we're supposed to find what's called the component form and the magnitude of a vector. So I'm just going to put this in perspective of a graph here. So on my graph, I've got a point at -1, -2/3, maybe somewhere in here, or -2/3, -1, excuse me. And then I have another point at 1/2, 4/5, and I'm not trying to draw too much to scale here, but maybe something like this, 1/2, 4/5. And here's an important concept of a vector. I asked, how do I go to Chicago? You tell me 70 miles, not enough information. You tell me you go 70 miles and then give me some degree measure from, or perhaps maybe say go due east 70 miles. Now I've got enough information. But um, where I start from and where I end, me going to Chicago is different than me coming home from Chicago. So that's why they talk about an initial point, a terminal point. Here is our vector, but it's directional. So how we represent this thing in component form, we get to use these cool little brackets. And it's really sort of just like an ordered pair. But we want to base that vector, we want to think about where would it go if, let's say, my job every day was to take this chair and slide it in this direction this far, wherever the chair is. What if the chair started at 0, 0? Then my slide would be out this far. And I'd really like to know the circumstances when I'm sliding it from 0, 0 rather than when I start the chair at -2, -1. So I still need to go this same distance, but where would I end up? Well, pretty easy to see. I started xy's at -2/3. I went to 1/2. So if I take 1/2 where I ended and subtract where I started from, -2/3, I get, let's see, that would be 3/6 plus 4/6, 7/6. That's how far I have moved this chair in this direction. So 7/6 is my move to the right in this case. Of course, if it was negative, it would be my move to the left. Likewise, I've gone up to get from here to here, or look at it this way if you like. We've gone up. How far have we gone up? And we can quickly see, well, if I take the 4/5 and subtract the 1, I had to go up 1 and then I had to go up another 4/5. So if I take my terminal point y value, 4/5, subtract my initial point y value, I get 4/5 plus 5/5, I get 9/5. That is the component form of my vector, or what I'm doing to my chair. Wherever my chair starts, I'm going to take it to the right 7/6 and up 9/5. That's kind of how we represent it as components, but really we're just sliding the chair along there to that terminal point. Okay, so pretty simple process to understand, I believe, and pretty easy process to go through as well. Now, as far as magnitude goes, magnitude is just asking how far did I slide the chair? And if I slid the chair along this line, creating this right triangle, 7/6 by 9/5, the magnitude is this distance right here. I'm going to call it R. So my magnitude becomes, it's just a real quick Pythagorean theorem problem. The magnitude, we would represent this, if I call this vector u, then my magnitude would be the square root of my x component, 7/6 squared, plus my y component, 9/5 squared, square root of all of that, and we represent magnitude with kind of like a double absolute value sign. So here is our component form, and I will leave this to the reader to determine what our magnitude winds up as. That's the beginning of our introduction into vectors. You're going to find that mechanically they're pretty easy to work with. We just have to learn maybe a little bit of the vocabulary so we can communicate. Okay, use the figure. We're going to have a couple of these because it's going to be interesting. You're going to see we have a vector u, we have a vector v defined from 0, 0. But this only asks about the u portion of this. The nice thing about vectors are very, very easy to work with and very, very simple to understand. In fact, if I just had you guess what 3u would do, you would probably get that at this point. But u is a vector that takes things from a position in this direction and in that distance. So what I'd love to do is copy and paste that vector and place it right here. That's u, if I have the angle right. And then, since I need 3 of those, I just start moving my desk again. Slid it from here to here, slide the desk another u, slide the desk another u. And if I keep that angle constant, there is our vector 3u. Pretty straightforward, pretty easy to predict. Okay, we'll look at another problem using this same diagram that incorporates v. So now this says I want a vector that gets the job done, that would be the job done if I use these two vectors. I slid the desk use vector, and then I subtracted from that, sliding the desk v. So I want to start out with sliding the desk across the room. I'm going to let u do his job. So there is our u. And now the desk is located here, and now I want to slide that along v. Go ahead and put that one in red. So we're going to slide it v. However, this is minus v, or like plus negative v, which means basically I want to, instead of pushing the desk across the floor, I want to pull it in the opposite direction. We really want to go v in this direction. So I would take this guy, cut and paste if I could, and there is our v. So our resulting vector from u minus v, sure, we could take the desk and slide it across here, slide it down here, but the resulting vector is the same thing as if we would have just started here and slid the desk to there. There is our u minus v vector. And one more. Here we're going to start by letting v do v's job, and v wants to take the desk, slide it up to here. Hopefully that's, work with me here, that's the same angle, that's exactly what we have going on over here. Same distance, same angle. And then I want to subtract half of u, and if u is this long, if I'm subtracting it, we're going in the opposite direction. I would want to be something like this, attached to here. So half u, if I can model that, might look something like this. So here's my minus 1/2 u. Here was my v, but my resulting vector is the same as just dragging the chair to right here, v minus 1/2 u. Really straightforward. Again, probably exactly what you would predict. But a frame of mind to be in is v minus 1/2 u doesn't really take our vector along this path. It really takes our vector along that path. It's really just one new job. It's one new vector. Okay. more real straightforwardness here. We have u and v defined. U's a vector that doesn't slide things to the right or left at all, but then slides them down 5. V is a vector that slides things to the left 3 and then up 9. And if you just had to guess, now our book has a page devoted to this. If you just had to guess what the vector u plus v would look like, you would probably say, well, kind of makes sense if first I slide things to the right 0 and then I slide things to the left 3. Total, I've slid things to the left 3. This is just 0 plus negative 3. If I start out with the y component by moving things down 5 and then I move things up 9, cumulatively, I've moved things up 4. This is just negative 5 plus 9. And we end, very, very simple, with negative 3, not 9. We end, very simple, with negative 3, 4. Okay. Not much to it, and probably exactly what you would suspect. So probably no way, knowing that you would miss B that asks for u minus v. Our x component is 0 minus our other x component, negative 3. Our y components are negative 5 minus our other y component, 9, for a resultant vector of positive 3, negative 14. Easy as could be. C. I want to double u and subtract 3 times vector v, and once again, exactly what you would think we would do. For our x component, I'm going to double 0. And then I'm going to subtract from that 3 times my other x component, negative 9. For my y component, I'm going to double negative 5 and subtract from that 3 times 9. And we end with positive 9, negative 37. And for D, again, exactly what you should suspect here. When we take vector v first and then add to it 4 times vector u, I get vector v's x component, negative 3, plus 4 times, again, u's component, 4 times 0, 0. Then I get v's y component, 9, plus 4 times u's component, 4 times negative 5, negative 20, for a resultant vector of negative 3 plus 0, negative 3, and 9 plus negative 20, negative 11. Compared to a lot of what we've been doing, not too bad. Okay, these problems are kind of cool here. So here we have use the figure and write the vector in terms of the other 2 vectors. So we have 3 vectors represented on this graph, u, v, and w. Please note the directions on those. I may have to emphasize those as I draw over those a little bit. But what this is saying is I want to get the job done that v does, but for whatever reason, v is not available. Perhaps we have an alligator, right? Man-eating alligator right here. It's a bad alligator. So we don't want to use v. V is off limits. That road is closed. So we want to do the job that v does, get from here to here, and I can use u and w vectors to do that. So my option, if I start here, I think the most clear option would be I could use the u vector, but I am going backwards u, and then use the w vector forward plus w. Note, we got an option to this. Algebraically, if we're looking over here, we could say, well, what could we write that then as w minus u? And sure we could. And that would be representative of, we start here, go out w, and come back, and I ran out of room here on my board, but come back this direction, our u value. And we create these parallelograms. So I think this is the most clear one. Why not just start here and track there? We go this way, we go this way. That's minus u plus w. Okay, and then it's just an example problem. Let me clear this off just a little bit here. I don't know if this residue that I'm getting here stays on the video portion of this. So if it does, I apologize for that. But anyway, I want to go, let's represent 2u. So 2u would do this job. It would go from here to here, and then it would go from here to, let's say there, I might be cutting it a little bit short, but I'm running out of room again. How could we use w and v and stay off that red u path and do the same job getting from here to here? Well, I could go over w. I could come back v. I could go way over w again and then come back v along that route where I ran out of room on my whiteboard. Okay, so that would be 2 units of going over w and then 2 units of coming back against what v wants to do, minus 2 units of v. Okay. Find the vector v with the given magnitude and the same direction as vector u. So again, here is our symbol for magnitude, kind of like these little double absolute values. Magnitude is 3. Let's take a look at u. U is a vector that would take my chair or my desk and it would slide it 5 to the right, 6 up to this point right here, 5, 6. And I note that real quickly, Pythagorean, 6 squared 36 and 5 squared 25, 61. This is square root of 61. But I want to be in the same direction as 5, 6 or vector u, but I want to stop before I get there. I want to stop somewhere maybe around in here where I'm just over 3. But one thing I note about these triangles, where this is 3, and I know everything about the other triangle, what I remember from geometry is no doubt about it, those guys are similar, and similar triangles have proportional sides. And proportion, just a fancy name for 2 equal ratios. Ratio, just a fancy name for fraction, 2 equal fractions. I'd really like to know what this value is and this value. So I'm going to set up my first proportion. X is in the same position as 5, while 3 is in the same position of root 61. Giving me, not equal to, but giving me x equals 15 on root 61, or 15 root 61 on 61. Likewise, y is in the same position as 6, while 3 is in the same position of root 61, giving me a y component of 6 times 3, 18, root 61 on 61, for a vector of x component, y component. And there's our vector. Okay, let's take a look at one that has a negative involved, so it's not just moving to the right and up. Okay. Now this notation, this is called a linear combination, and this I and j are not variables in vector land, and unfortunately I is not the square root of negative 1 in vector land. I is this specific vector. It's called a unit vector for obvious reasons. It moves 1 unit to the right. And j, you could probably guess, is a unit vector. It moves up 1. So this is linear form. If I wanted to put that in component form, it would be this simple. Component form, it's just 2 to the right and 3 down. So once again, it's just kind of a vocabulary thing. So if you want to work with that, that's great. Now this is the same problem as the last one. 2, negative 3 would get me somewhere down in here, and we see Pythagorean, 9 and 4, 13. This length is root 13. but I want to have a magnitude of 10. Same direction, but I might want to be way down here 10. And once again, we have these similar triangles. So I'm going to separate those over here just for clarity. Let's go with our, here we have, whoops, 10 is not over here. I apologize, that 10 is here. Here we have a magnitude of 10 or a hypotenuse of 10 as opposed to this triangle where we are 2, 3, and root 13. So we're in the exact same ball game we were in before, where now I just want to know what this x value is. I want to know what this y value is, and I think I'm just going to set this up and let you conclude this one. Maybe I'll wrap it up. X is in the same position as 2, while 10 is in the same position as root 13, giving us x equals 20 root 13 on 13, while y is in the same position as 3, and 10 is in the same position as root 13, giving us the y component of 30 root 13 on 13. So if I was to put this in component notation, I would just group these together. But because we started in this linear, I think I'll go ahead and write this linear, but it's as easy as this. V is equal to 20 root 13 on 13i. And by the way, this is a -3, so I apologize for that guy. What does that affect? -3, -30 here. And then I would have a minus 30 root 13 on 13j. Okay. Okay, then the initial and terminal points of a vector are given. Write the vector as a linear combination. That's the form we just got done wrapping up with of the standard unit vector. So I have a vector that starts me at -6 and slides me over to 0. It has moved. Its components are 0. Its x component 0 minus -6. Its y component 1 minus 4. So that would be in this form, 6, -3. But this is component form. In other words, I would be sliding a desk 6 to the right, moving it down 3. I slid it 6 to the right. I moved it down 3. And we just want to represent this in linear combination form with I and j. So this is as easy as this. Let's name this guy vector v is equal to 6i minus 3j. And as it stands at this time, you have enough information for you. You should be able to battle through 1 through 75 odds pretty quickly. But we're going to come back and discuss how we apply these things to story problems. Have at it and try 81 through 87. I may add a couple problems to that, but that's going to be tomorrow's discussion.